In fact, I would highly recommend that you do all the calculations last. Just try to do principal concept, equation, keep it till the end when you have more. Well, if you have time, then you can put in the values because just 20% of your 10 to 20% of your course credit is question credit is the final answer. The 1.5 mg sports car, 1.5 mg means 10 raised to 6 mega is 10 raised to 6, that's grams, and so that's going to be 1500 kgs. Sports car has a tractive force of 4.5 kilonewtons. If it produces the velocity described by the VT plot shown here, plot the air resistance versus time for this time period. So the tractive force F is a force which is developed on the tires of the car when you accelerate or when the engine works to power the car, right? So that's the force which is pushing the car forward. Okay, there's going to be resistance, wind resistance, so on. That is all marked as R. We got to find R such that we'll produce this particular VT profile. Okay, so again, I would go by this. First of all, if you go through this list, first one, is it a kinematics problem? Well, it is not a kinematics problem because you're given the mass. Are you told to find a velocity when the object moves a certain distance? A velocity is a function of displacement. That's clearly not the case. Are you asked to find the velocity after a certain time? So number 3. That's also not what is asked. You're told to find the reaction force, and so you're left with 4, which is you got to apply Newton's laws to solve this problem. So this is a problem on particles and not rigid bodies, because if it was a rigid body problem, then hints would be you would be given the inertia or you would be given dimensions for that object. Okay? You're not given both, so it's a particle problem. So it's actually chapter 30. Okay, so we need to find R. And we can use Newton's laws. So whenever you have to use Newton's laws, I highly recommend drawing a free body diagram, even if we do not ask you to draw one, because that usually carries partial credit. Reaction force opposes motion. The traction force helps to move forward. In this case, the acceleration is obviously going to be to the left. And so equations of motion. F minus R equals mass times acceleration. Okay. Should there be a normal force? Absolutely right. So so it's a good practice to draw all the forces, even though I'm not going to use N and mg in my equation. I still need to draw. That's right. So this is the equation of motion in the x direction. So Fx equals max if you think x is to the left. Okay, so let's see what's given. F is given, R is the unknown, the mass is given, the acceleration, is that given to you? You are given the acceleration because you are given the velocity time plot. Okay, so A is given. Let's find A, because once we know A, we can find R. So V is minus 0.05 t square plus 3t, and so acceleration is the rate of change of velocity, so that's minus 0.1 t, because derivative of t square is 2t, plus 3, and so F, which is 4.5 times 10 raised to 3 minus R, equals the mass, which is 1500 kilograms, minus 0.1 t plus 3. So R is 4500 minus 150, plus 150t minus 45. Is that right? R equals 150t is what I get. Yeah. So you asked to plot the resistance as a function of time. Okay, so we got to draw the equation R equals 150t. It's clear that if you put t equals 0, you get R equals 0. So that passes through the origin. And then that's the equation of a straight line with a slope of 150. So that's 150. Okay, any questions? Questions? Okay, so let's move to the next one. So force of 250 newtons applied to the end B. Determine the speed of the 10 kg block. So we need to find the speed. This is 10 kg block. We got to find the speed when it has moved. So when A has moved, let's call that 1.5. I wrote delta YA because it's the displacement. Okay, change in it's basically measured as final position minus initial position, which is the differential. Okay, starting from rest, which means that V equals 0 when or another way of writing this is, let me write it this way. Initially YA equals 0, the final YA is 1.5, which also means that the delta Y is at 0, YA minus YA at 0, which is equal to 1.5. Okay, so how do we solve this? Well, going back to this, are you asked to find velocity acceleration of a point given the velocity acceleration of another point? In this case, you're told to find the velocity of point A, but you're not given the velocity of point B. Right? If you're given the velocity or acceleration of point B, then yes, this is a kinematics problem and you should just use kinematics to solve it. That's not the case. So we can rule out one. Next one, number 2. Are you asked to find velocity as a function of displacement? And the answer is yes, right? It's right here. We need to find the velocity when the displacement is 1.5. So it fits 2, and so we need to either use conservation of energy, and we use conservation of energy when all the forces are conservative forces, and there are only 2 conservative forces. There is force due to springs and force due to gravity. In this case, there's only gravity. Well, that's not true. There's capital F, right? So it turns out that capital F, the way it is defined, is a constant it is actually a conservative force. So you could treat this problem as having all conservative forces and solve it that way. But if you want to be technically correct, then you can actually treat F as non-conservative, which is not true, it is actually conservative, and use the principle of work energy. So both of these methods, work energy or conservation of energy, will work. And the reason why conservation would work in particular, even though F is an external force, not gravity, not spring, is because the work done by the force F is F times delta x, or displacement, and that really depends on the final and initial positions, right? A conservative force is a force in which the work done depends only on the initial and final position. So if you move, F is applied, it moves the point B from here to here about 1 meters over here, or 1 meters down there, or 1 meters up there. It doesn't really matter. It's going to be the same work done. So in that case, it's actually a conservative force. So you really have an option of using either of the two. So let me do it in a way in which the book has not done it. The book solves it using so yeah, book actually uses principle of work energy. Let me stick to that because that's the right way to do it. I just don't want to confuse you with the incorrect way of doing this. So work energy, and the reason is because as there is an external force F. Okay. Now, if I replace that F with, it's 250 newtons, but I said the force is 250 times time or 250 times displacement, but it's not a constant, then that force is no longer conservative, and you cannot use conservation of energy. You'll have to use principle of work energy. Okay. So as long as F is constant, it is a conservative force. That's important. So let's use principle of work energy just to be on the safe side. That makes no assumptions about F. So that principle states that T1 plus the work done, all work done, equals T2. Okay, so the setup starts from rest, which means T1 is 0. Let me write T2 because that's easy. It's simply half mass of A, velocity of A squared, or V squared, where V is unknown. That's what is asked. Okay, I need to write the work done, and I'm done. So work done will be, so the best way to figure out the work done, in my opinion, is to draw a free body diagram. Okay, once you draw a free body diagram, you see all the forces, and the work done is basically force times displacement. So I could potentially draw a free body diagram of A and of each of those pulleys, but moment I draw individual free body diagrams, what will happen is I will cut the strings, and that'll introduce tension between the two pulleys. Okay, and which means I have to then solve for the tension and then find the work done due to the tension. So I want to try to avoid finding things I do not care about. So I do not care about the tension, evaluating the tension in the string. So what I'm going to do is, instead of drawing a free body diagram for individual elements, I'm going to draw one free body diagram for the entire system, and that will become useful because then it's not, I don't need to, I would not have to find the work done due to those forces which I would have introduced had I cut this over here. I would have had a force here. I don't want those forces here. So right now there are just three forces, assuming that the pulleys are massless. Okay, and I need to write the work done. So work done is force times displacement. Okay, I need to introduce a variable for the displacement. So what I'm going to do is, I would need this anyway. Let me choose a datum here. and write this as YA and this as YB. Okay, and so the work done is going to be the force times the displacement of YB. Okay, now my convention is, well, the way I've shown it, YB is positive downwards, and so F is positive downwards, delta YB is positive downwards, and so when you take the force times delta, it's going to be positive because both of them are in the downward direction. Similarly, MAG is downwards, delta YA is also downwards. Okay, so that's my equation. There are a lot of unknowns here. Mass is known, F is known, MAG is known. I do not know these things, but I do know delta YA. So I do know delta YA, but I do not know delta YB. Okay, so in order to find delta YB, now this is a problem involving a mixture of two chapters. In order to find delta YB in terms of YA, it's a kinematics problem, something which you've learned in the past for solving displacement of A given the displacement of B or vice versa. So let's do the kinematics. Okay, and this kinematics involves finding the length of the cable, differentiating with respect to time, or take the differential, and that will give you a relation between the displacements of A and B. So length of cable, which is all this, equals YA, which is the left side, and then there's YB and YB on the right side, so it's 2YB. So now many people get confused. In the past I've seen people get confused with differential and derivative. They're pretty much the same. So let's take the derivative because that's what we're used to. So L dot, which is 0, equals Y dot plus 2Y dot B. Okay, but what is the derivative? What is the definition of a derivative? It is basically delta YA divided by delta T, right? Rate of change of position plus 2 delta YB delta T, and that's equal to 0. So another way of looking at the same equation is you can multiply both sides by delta T and you can cancel it off, and so we can write delta YB equals half delta YA. Okay, so the differential and the derivative are pretty much the same. You don't get confused. This is comes again every time we teach it. That is how did you get delta Y from Y dot? And that's how we get it. Okay, so now we can put this right there. Let's call this 1. $250. Delta YB is minus 0.5, delta YA, which is 1.5. Plus MA is 10, 9.81, delta YA is 1.5. Okay. Hold on, I think I made an error. The sign is an issue. So when it has moved 1.5 meters starting from rest, so they do not say whether 1.5 meters is down or up, and I got to first figure that out because I need to put the right signs. The question is this positive or is it negative? And that actually will affect my answer. So what do you think? It's upward or downwards? And how would you figure that out? So the way to figure that out is find the values for F and MAG. MAG is 10 times 9.81, so 98.1. Okay, so if that's 250, that's 98.1. We would ask ourselves, will this move down or this point move down? If this moves down, then there will be a positive. If that moves up, it's going to be a negative. Okay, and so you could do this calculation in your head, or you might need to draw a separate free body diagram for these two things. So basically, that free body diagram, you don't have to do an acceleration analysis. You can just do a static analysis. If you cut the string here, then you have F equals, let's call that T1 and T1. So F equals 2 times T1, that is static equilibrium, and then T1 equals 98.1, right? So 98.1, 98.1, that's 196, but that's 196, of course, is less than 250, and so it moved down, right side will move down. I'll repeat it on this side. Okay, how do you figure out if this is going down or this is going down? Here's how you do it. Okay, you go to either draw free body diagram or do it in your head. If you cut the string here, draw free body diagram for this particular pulley, it's going to have T1 and T1, upwards, of course. So F would be equal to 2 times T1, because there are two forces, T1 up. With that T1, which is over here, the same as the T1 over here, so 98.1 equals T1, but we also wrote down, or thought about it, 2T1 equals F, which is 250. So 2 times T1 is 196.2. So there's 196.2 pulling and there's 250 pulling down. Clearly 250 is more than 196. So F will move down, which means A would move up. And so that sign over there is negative because my convention is YA is positive downwards. If it moves up, it's going to be negative. So I actually made an error here. I just have to put a negative sign. So there's a negative sign here and negative 1.5 equals half times 2 times, so 10 times v square. Let me just draw this over here, what I just said, MAG, and then we'll have T1, T1, 250. So twice T1, which is equal to 196.2, is less than 250. So A moves up. Okay, so if you solve for V from that equation, you should get 2.84 meters per second. Okay, so there are a lot of things going on in this question. If you think of it, we use work energy, we had to do kinematics, and then we also had to do sort of dynamic F equals ma analysis to figure out the direction. By the way, you could totally solve this problem without invoking work energy. If you drew free body diagrams for block A, for the pulley B, and just basically this free body diagram here, but showed the acceleration, you can solve for the acceleration first, the acceleration of block A. Once you know the acceleration of block A, you can find the velocity of block A because velocity and acceleration are related by a simple formula. In this case, acceleration would come out to be constant, and so the constant acceleration formulas are valid. Okay, so I'll mention it again. Even though there are lots of steps here, you really need 1 and 4. You can solve all questions using 1 and 4. You do not need 2 and 3. Okay, 2 and 3 actually are derived from 4, Newton's laws. Okay, what 2 and 3 helps you is that sometimes it's much faster to solve problems if you invoke 2 and 3. For some things, however, there are no options like well, that's not true. Everything actually, yeah, everything comes from Newton's laws. 2 and 3 come from Newton's laws. If you look at the book, there's a derivation which shows how Newton's laws equate to conservation of energy or work energy and so on. Okay, any questions on this? No questions? Okay. Okay, so next question. Determine the acceleration of the 150-pound cabinet and the normal reaction under the legs A and B if the force P is 35 pounds. The coefficient of static and kinetic friction between the cabinet and the plane are 0.2 and 0.15. The cabinet's center of gravity is located at G. Okay, so back to the sheet. First of all, is the kinematics problem. Are you given acceleration? Are you told to find acceleration or velocity given velocity acceleration of some other point? That's not the case. In fact, you're given the mass of the cabinet. So that's a hint. That's not a kinematics problem. Are you asked to find velocity when the object moves a certain distance? Number 2. That's not the case there. You're told to find the reaction forces at A and B. So that's not the case. Go to 3. Velocity is a function of time. That's not true either. And so you have to go for 4, which is use Newton's laws because you're told to find forces. Okay. So we got to use Newton's laws. So when you use Newton's laws, you got to think about free body diagrams to show that. So let me draw a free body diagram. Okay, so one thing about this problem is that I've not done a problem like this before in the class, nor I don't think I've assigned any problem. Okay, this is a problem which involves, well, it's like a rolling sliding problem. Well, you do not know if it's rolling or if it's sliding. First, you start assuming it's rolling, and then that's not true. Then you do sliding, right? Similar to that, this problem, you do not know if the block, if the cabinet is moving with a steady state acceleration A, or it is just beginning to move. Okay, and what distinguishes the two events is that coefficient of friction. So when the object is just about to move, so when you keep increasing the force P, some point the cabinet will begin to slide, right? So the question is P big enough for it to slide? The other thing which can happen is it could tip. Right? Instead of sliding, the force P is so great that it actually tips. So first we got to rule out tipping. Okay, and so what we do is we try to find P such that we find the minimum P so that the block will just begin to slide, or in other words, first find P needed for the cabinet to begin sliding. Begin sliding is given by the fact that A is close to 0, or it's actually 0, and the coefficient of friction is mu s. Right? When the object is static equilibrium, the force which prevents it from moving is the coefficient of static friction. So when A is 0, mu s is what you've got to use. So one thing which I was missing in this free body diagram is the friction force. So friction force at A and friction force at B. Okay, so in this case, friction at A equals mu s times NA, and friction at B is mu s times NB. That's the forces we'll use. So what I'm going to do is I'm going to try to solve for NA, NB, and P. Okay, and I'll make it clear what it means to slide, what it means to tip, when after I solve for NA, NB, and P. Assuming A equals 0. Okay, so three unknowns, NA, NB, and P. I got to generate three equations, and the way I'll generate three equations is F equals ma in the x direction, F equals ma in the y direction, and torque equals I alpha. This is 4B. Okay, 4B because, well, it's a rigid body. It's a rigid body because you can see that you're given the dimensions 4 and 3.5. Only for a rigid body will you be given the dimensions. So let's use Fx equals max. That gives me P minus friction force at A minus friction force at B equals 0 because acceleration is 0. So P minus mu s NA minus mu s and B equals 0. That's first equation. Second equation is Fy equals may. So that gives me Na plus Nb acting upwards minus Mg equals 0. Okay, and the third equation is torque equals I alpha, but since we assume it's not tipping or the angular acceleration is 0, torque, the net torque or net moment is equal to 0. I think I wrote M. So let's do moment about G. G is this point. So we have P times 4 minus 3.5, so 0.5, and that about G, that force is going to create a clockwise torque, so negative. NA acts at a distance of 1 feet, so NA times 1. About G, NA produces a clockwise torque, so negative. NB is to the left. It also has a momentum of 1. NB is producing a clock and counterclockwise torque about G, so it's positive. And then friction force, Fa and Fb, both of them are, well, they're acting, G is here, they're acting this way, and so they're going to create a clockwise torque about G. So it's essentially Fa plus Fb times 3.5. Momentum, and so negative for clockwise torque. So FA is mu S N A and FB is mu S N B. So equations 1, 2, and 3 are three equations involving three unknowns, P, Na, and Nb. You can solve for those three. If you solve for solving 1, 2, 3 gives me Na equals 15, Nb equals 135 pounds, and P equals 30. So we can note two things here. Na, Nb are both greater than 0. Okay, the forces are positive. If the forces had gone to less than 0, when will that happen? That can only happen if the cabinet is going to tip, right? One of the normal forces is going to go to 0. So if both of them are greater than 0, the cabinet does not tip. Also, we notice that P, which is equal to 30, is less than what force is applied by the person. The force applied is 35, right? Actual force. So what it means is that you require a force of 30 pounds to keep the cabinet in static equilibrium when the coefficient of friction mu s prevents you from sliding it. Okay, but the force which is applied is greater than 30, which means that the cabinet is going to slide and not going to be in static equilibrium. Okay, questions? So because of this, cabinet will slide. Okay, so it's not tipping because normal force is not 0. It will slide because the force P which is applied is greater than what P is needed to keep the block in equilibrium. So what we do is we got to resolve this problem assuming that the acceleration is not equal to 0. Okay, resolve unknowns now are going to be Na, Nb, and acceleration because the force P is given to us 35 pounds. So we do the same thing, Fx equals Max which gives me, it's going to be the same equation as before except that we need to replace the coefficient of static friction with kinetic friction because now the block is moving to the right with a non-zero speed. So this will give me Fp minus mu k Na minus mu k Nb equals mass times acceleration. Fy equals May would give me Na plus Nb minus Mg equals 0. And then the last equation is Mg equals 0, gives me, it's basically the same equation, P times 0.5, except that the friction force is replaced with mu k. Mu k Na plus Nb times 3.5 equals 0. So solve those three equations. You get A equal
Nb positive for both.
Nb, yes. Solve for A, Na, and Nb. A is 2.68. Na equals 26.9, it's positive, and Nb equals 123 pounds. Okay, so this is, as I said, so I've not saw this type of question in the class. I don't think I assigned it in the homeworks. You might want to pay attention and understand this question, how it is done. It's very much like rolling sliding. You assume rolling, and then that's not true. You do sliding. In this case, you start assuming it's not sliding or it's tipping. Solve for forces P and NA. If they're positive, the reaction force is not tipping. If the force applied is greater than the force which you get, it's sliding, and then you solve the sliding part. Okay, so